Once again, folks, good afternoon. This time around, I'm proceeding with question number 12 and 13, which was covered in February, March 2025 paper. Yeah, I hope you find this interesting. All right. Um, let's see. We're given a problem here. Our interest is to calculate the total surface area. So total surface area, if I can put a simple picture of a cone, it's a shape like that, where we have got a slanting or sloping edge, we call it L, in this radius, we also have a circular part here, which is um, R. Um, Now, if we're interested in the total surface area, we have a formula. So we'll say surface area is equal to um, pi r L, that's from the circular part, um, plus pi r squared when we look at the circular parts as well. So pi r L and pi r squared. Let's see. I think these formulas will find them here on the home page. We don't want to make a mistake. The curved surface area of a cone. So we have the curved surface area here. It's shown. So I think we're okay. Can go back to our question where we were saying um, that should be our formula. Now, when I'm doing my substitutions, I'm now saying can factor pi because it's common on both plus radius I'm given there is 5 multiplied by the slanting or sloping length, which is 12 plus, now this time around I just want radius squared. So when I simplify, I'll have pi here inside the brackets. I'll have 5 times 12, that's a 60 plus, or I have the 5 squared, that's 25. So I'm allowed to simplify these two. 60 plus 25, that's 85 pi square centimeters. I think that's what we might have for this particular problem. Right. Moving on, we have got number patterns there. Table shows the first 5 terms of sequence A, B, and C. Complete the table to show the nth term of each sequence. So I'm going to look at the first one. I've got 5, 12, 31. It looks like this pattern or sequence is growing too quick. So what might I try to inspect? Let's try and check. It looks like it's cubic. And when I say cubic, I'm saying if I say 1 squared, what happens? I mean, sorry, 1 cubed. And if I say 2 cubed, 3 cubed, just trying to inspect what will happen. So 1 squared gives me 1, and 2 cubed gives me 8. 3 cubed gives me 27. So when I try and check the difference here, it looks like the difference is there 4. Even here between 8 and 12, it looks like the difference is 4. 27 and 31, the difference is still 4. So I can come to say the nth term here is n cubed, where n is the position. Then after that, we add a 4. Now I'm on the second pattern, which is fraction. So what I'll do, I'm going to look at what's happening on the numerator. 10, 9, 8. Wow, it looks like our difference is -1. And normally with these arithmetic patterns, we then say, okay, that's minus n the position. Then what will be the next step? The next step is to try with 1. So if I say -1, I check there, I've got 10. So it looks like 11 minus n might be our formula. Because if I say 11 minus 2 on the second part, it will give me 9. So on my numerator, it's going to be 11 minus n. Then when I go to the denominator, it looks like from 3 to 4, we have got an increment of 1. So it means it's 1 times n, it's just 1. But when I try the first position to give me 1, but I'm interested in 3. So if my position is 1 and I need 3, I'll add 2. So I'll come here and say that this will be n plus 2. Now I'm on the last sequence where I'm seeing clear that we have 4, 8, 16, keeps on going like that. What might be queasy? What's queasy here is looks like all these numbers, they can be written in exponential form where the base is 2, but we are raising these 2 to a certain n position. If I try with 1, it looks like 2 to the power 1 just give us 1. Oh, the idea was, can we get a 2 on the numerator? So that can be n plus 1. So if I try it on position 2, it will be 2 plus 1, which will be 2 cubed, giving me 8. So the formula here will be 2 to the power n plus 1. I think that was it on the next two questions. I hope you found them interesting. We'll proceed with question 14 just after this mini break. Thank you.